Okay, hi. So tomorrow is the exam, and I hope everyone has seen my video I posted on Monday. Um, I redid critical resolve shear stress because I wanted to clarify a couple things. So if you have any questions about that, you can check that out. If if I'll be more than happy to review the topics of the exam if anyone has questions. But I think we've done a pretty thorough job of covering everything. So unless you give me something to talk about, I'm going to move on to new material because there's really not that much time left in between. There's a lot of time between the start of the class and the first exam, but the second exam is going to be a lot quicker. So we have to cover a lot more material. So if anyone has any questions, we can go over them. Else, I'm going to continue on. Okay, so I guess we'll just continue. So can you go through the ductile to brittle transition? Okay, yeah. So yeah, sure, why not? Okay. I haven't gotten to watch yesterday's lecture yet. Is the exam during? Yeah, so the exam should be during class time tomorrow at 8 a.m. Yeah, that's my understanding. Okay, ductile to brittle transition. Let's do that one. Okay, what else is going to have to do? Right, so when we talk about ductility or brittleness, we're talking about a material's ability to bend or to respond to a tensile stress through elongation, right? So when we stretch two atoms, if we model the atoms as hooks or like a spring, they will stretch to some point, and then they will, when you relax, they will relax back to the original positions. And you know, as we allow these materials to bend, we could induce plastic deformation, which is permanent movement of these atoms, and then the atoms break bonds and form new bonds as they move to new positions, right? And so if we think about different materials in our lives, certain materials are bendy and certain aren't. So like plastic is very ductile, it's very bendy. But we don't think of plastic as ductile. We think of ductility as something that we apply to metals. So like a like paper clip, you know, or aluminum foil is very bendy. It's very ductile. And so why is that? And that's because we could induce a lot of plastic deformation into it before it breaks. But at the same time, you know, every time we induce plastic deformation, we make it a little bit more harder. So this goes back to this idea of strain hardening. So I guess one way to discuss it is like, these novels really suck. Cool. Okay, this is better. So we have material A and material B, right? These are stress strain curves, and what we can see is that material A has a high tensile strength, right? It has a high yield point, but very little ductility, very little plastic deformation can occur. But on the other hand, we have this material who has a lower yield point, but has a lot more room for ductility or plastic deformation. And so what happens is as we cold walk the material, cold walking was one of the 4 ways we can strengthen materials. If we cold walk the material, is we induce some plastic deformation to this point, and then when we relax the material, we've induced this permanent strain, right? But now our yield point has increased. So by inducing a tensile stress, we've performed this much plastic deformation, right? And then now we have a stronger material, but our remaining plastic region has shrunk as a result. So it has become less ductile because we've already used up some of that ductility, and we can continue to stress and relax and stress and relax, right? And if we get to this position here, right, we have this strength, but now we only have this much ductility left. We only have this much plastic deformation left. And at this point, you know, we've deformed the material so much, we've cold walked the material so much, it's hard to make the argument that it is still a ductile material. So it's now brittle. So the ductile to brittle transition that occurs in metals is very gradual, but it's a result of inducing plastic deformation into the material. And so let me make sure I get this right. So in most cases, when we think about very ductile metals, we're talking about FCC materials. So things like aluminum, copper, even things that have the base centered cubic unit cell, and they tend to be more ductile than atoms that have the BCC or body centered cubic unit system. So that is one way we can differentiate between metals even, or get a hint at the crystal structure of a material by investigating the ductility of the material. That was a great question, so thank you for that. Okay, cool. So posted to Blackboard is a list of questions for the second exam. And the second exam always begins to branch out away from just metals per se to different materials classes, specifically ceramics and polymers. And I mean, we have talked about ceramics a little bit, but polymers are kind of new and interesting, and polymers kind of break a lot of the rules that we've established. And so I think today it would be a good time, because the exam is coming up, we don't want to introduce too much information, but I think today would be a good time to discuss polymers and relay the foundation to begin to talk about why polymers are so different and unique compared to metals and ceramics. So let's see. So here we have like a simple schematic of a metal or ceramic, right? Where we have one atom and it's bonded to all the atoms around it, right? And these bonds we call primary bonds. There's some form of, electrons are moving between atoms or electrons are shared between atoms. There's some a very explicit sharing of atoms between these electrons, right? And we discussed how in metals we have metallic bonds, and how in ceramics we most often have ionic bonds. So when we think about, ionic bonds, there are bonds that are very discretely quantized. And what I mean by that is that this atom will be positive, so this atom will be positive, and this atom will be negative, right? So this atom will have one extra electron, this atom will be will have a deficit of one electron. But that's what they need to fulfill the octet rule or to be more energetically stable. Likewise, metallic bonds are a very interesting class of bonds where electrons are just going all over the place, right? Because there's so many orbitals open for them. There's so many positions that, electrons really are free to go wherever they want. So the third type of bonding we have is covalent bonding. And so covalent bonding, let's see. So during covalent bonding, if we have a carbon atom and another carbon atom, they will share electrons between each other. So half the time, the electrons will be on one atom, half the time the electrons will be on another atom. And so polymers have covalent bonds, and the polymers are designed of many monomer units bonded repeatedly to each other in a long chain. So in this way, they form a repeating pattern, but it's linear and not three-dimensional, right? So when we talked about unit cells and crystallography, we were talking about three-dimensional patterns, but in polymers, we're talking about repeating units. And so these units can take many forms and many shapes, but one of the most common one is polyethylene, right? So that's probably what your, your takeout containers are made out of, polyethylene. And it looks something like this, right? And so when you have two polyethylene molecules together, right? Like this. if we induce a chemical reaction, we can break this bond, those two bonds between these carbons. If we use a chemical reaction or a free radical of some sort to break this bond, then we can form a bond between these two carbons, and then break this bond and form a bond between a carbon here, and then break this bond and so forth. And then break this bond, here, et cetera, et cetera. And what we get is this long chain of hydrocarbons composed of this monomer unit. Now, this is all well and good once we, we have one polymer strand, right? That's interesting, I guess. But so what happens when we have two strands close to each other, right? So oftentimes we draw polymers like this. Right? Well, each one of these vertices denotes a carbon, right? So this is actually H2, like CH2, CH2, et cetera, right? So now, if we have a second chain that exists like this, right? So now we have two polymer chains existing in space close to each other. But along the polymer backbone, right, the backbone of the polymer, we have these very strong covalent bonds. These bonds, they're covalent, they're orbitals or electrons are shared between two carbons. And between them, between the chains themselves, we're going to have hydrogen bonding. Right? And hydrogen bonding is a form of secondary bonding. So it's basic, hydrogen is the first element, and it has a positive charge, it's just one atom, it's one proton and one electron, right? And so it has a positive charge, and positive charges are loosely attracted to negative charges. So the positive charges between the hydrogen atoms and the localized negative charge on the carbon maybe could introduce some form of attraction between the two polymer strands. Right? And so what we have is a loose attraction between the two strands that kind of keeps them in place with each other. It kind of keeps them aligned. But, when in this state, we have the strong covalent bonds and then the loose attraction of the hydrogen bonds between the two strands. So if you induce any strain whatsoever, any force whatsoever, the first thing that's going to break are these hydrogen bonds. These hydrogen bonds aren't going to do much in keeping the structure intact. So they're really, and so in that way, we like to describe, polymers as a plate of spaghetti, or a bowl of ramen, or your favorite noodle, really just, they're constantly sliding past each other in this web of entanglement. It's like very, I'm really hungry, so yeah. But I need breakfast. But anyway, so in this way, this is distinctly different from metals, right? Because metals, in every direction, the atoms are bonded metallically, or the atoms have similar bonds in every direction. And it doesn't matter how you orient your crystal because your crystal is repeating, right? But here in polymers, we will have, it's very important the way the crystal is aligned and the way the polymer, the orientation of the polymer chains. Moreover, like when we talk about crystallinity, this idea of crystallinity in a metal, you know, it's very much like, okay, this is a crystal and it's all lined in one way, and then the crystal is a different grain, it's lined this way, but they're still crystals, they're still very organized. Polymers do not have to be organized at all. And in fact, it's very hard to organize polymers. And so what we end up having is, you know, we have these long strings of polymers, and oh my God, the majority of the space is amorphous, but we might have this, you know, region of crystallinity here, or we might have a region of crystallinity here. So in an overall amorphous macrostructure, we could have pockets of crystallinity. And so that's why we often describe polymer crystallinity as a percentage, where 20% of the polymer is aligned very organized, in an organized fashion, and 70% of the polymer is not. And so depending on crystallinity, you know, crystallinity can increase or decrease your mechanical properties. Depending on how we process and form our polymers, we will also induce different degrees of crystallinity to tailor all different material properties that we're trying to target. One of the biggest ways crystallinity can affect polymers is through like opacity. So, you know, most plastics are see-through. A lot of plastics are see-through, right? And that's probably because they're amorphous, you know, light can just pass right through them. But if we induce a crystallinity in our polymers, now light gets scattered when it tries to pass through the polymer, and it becomes opaque or doesn't become transparent, you know? So that is another way we try to engineer polymers. That's really important, you know, because you want your phone case to be transparent, or the protective covering we put on our phones, it can't, we have to see through it, right? So that's one way that polymers differ from metals. And then the other way, and what we see oftentimes, okay. So this could be a metal, and this is a polymer down below. And so what we see is the polymer has a lot more plastic deformation that can occur, but it has a very low Young's moduli. And that's exactly for the reason that we just discussed, where we have regions of, you know, we have regions of strong covalent bonds and then weak secondary bonds between the chains. So those weak secondary bonds are so easy to break. And once we break those bonds, polymer chains start moving. They start sliding past each other. And in that way, we've permanently changed the structure. We've permanently deformed the structure and induced plastic deformation. So it's very easy to break plastic, to induce plastic deformation. But good morning. But a lot of energy will be required to eventually break the polymer bonds, because, you know, those covalent bonds are so strong. And so one interesting way that we can track this is by looking at the strain rate or the speed at which we pull on the material. And I think this is interesting because it kind of relates to this ductile to brittle transition, but for a different class of materials. So just to be clear that this polymer stuff isn't on your first exam, but you know, it's kind of wrapping the concepts together in a neat way. So the idea being that if you pull on a polymer or you stress the polymer very quickly, it will act in a brittle fashion. But if we pull on the polymer very, very slowly, it will act in a very ductile way. So if we pull on a, like, I don't have anything to break. You have like a eraser? Gum. Oh, gum. Yeah. Okay. Gum. So gum is a natural polymer. This is perfect. Okay. So gum is a natural polymer. Most polymers we're going to be talking about are synthetic, but gum is natural. So that's cool. It comes from a tree. Okay. So this is great. Oh, sorry. Ew, this kind of goes. So if I pull this really quickly, let's see if I can do this. Oh, it broke, right? Wow. Because I poured the gum so quickly that the bonds just broke immediately, right? The time scale didn't give the polymer chains enough time to like react and stretch out, so they just had to break. But if I pull it very slowly, oh my God, this is disgusting. Okay, it's not really walking. But if I pull it very slowly, I guess you could see that now there's a lot more elongation induced because like I can pull this, I can pull the strands close. The strands have enough time to react to the stress. And as a result, you know, the polymer elongates a lot more. So my hands are all sticky. It's no, it's the thought that counts, you know, it's okay. So this is very fast. And then this might be a medium speed. And this is a very slow speed. So what we have is we have polymer chains of the same composition pulled at different rates. And they, as a result, you get lower tensile stresses, right? But much longer plastic deformation when you go to slower speed. And there's a lot of videos. So I wish we were in person, because if we were in person, we could break some things and it would be fun. But I'll find a video for you guys to show this, or maybe I'll think of a way to demonstrate it. But it's very interesting. And it's like, we see this all the time when, oh, this is going to be gross too. Like, so if you have a pen and you chew on the pen a lot, or the pen cap, like it changes color and it becomes like longer, right? And that's you inducing plastic deformation, and you're doing it very slowly, right? That's a very slow process, because like I don't know, like you're doing math or something and you take a whatever. But it's so as a result, that pen cap or that pen can deform a lot because it's done over a slow time. Well, you know, if you just snap the pen in half, the pen would break almost immediately because the stress was applied in a very short time. And that has to do with the fact that polymers, you know, have these two types of bonds. They have strong covalent bonds along the polymer backbone and weak secondary bonds along in between the chains themselves. Glass transition temperature. Okay, so the other thing we should talk about, we talked about the structure of polymers, we talked about stress strain response of polymers, and the other thing we should talk about is the glass transition temperature of polymers. And then ceramics also have a glass transition temperature. But first, let's talk about it in polymers. So, you know, polymers are bendy, polymers are plastic, right? And the big selling point is the ductility. But, you know, a lot of times that is temperature dependent. And ductility is the movement of polymer chains past each other. So ductility is the movement of atoms. And when we discussed diffusion before, we said that the movement of atoms is largely dependent on temperature. So the higher the temperature, the easier it is for atoms to move, right? The more energy atoms have, the easier it is for atoms to move. So there is a point, you know, above which, in that temperature range, the polymer is ductile, it's bendy, it's flexible. But if we go below this temperature, then the polymers, the atoms struggle to move because they don't have enough energy to freely move past each other. And this is called the glass transition temperature. And below which, below the glass transition temperature, polymers become brittle, right? So this is also seen in ceramics a lot of time, you know, but it's kind of like, so we live within the realm of the polymer glass transition temperature, right? Because polymers generally exist on all temperature scales, right? So we're talking about maybe negative 20 degrees Fahrenheit, we could have a glass transition temperature. And humans live in those ranges. But the glass transition temperatures for ceramics are very high, right? And that's why ceramics in our experience are brittle, because if the glass transition temperature of a ceramic is 1,000 degrees, I'm not going to 1,000 degrees. I'm not going to live in that world, you know? So in my world, ceramics are all brittle. And so it's interesting because for the longest time, this idea was, you know, theorized about for ceramics. And I guess someone somewhere proved that it existed, but it wasn't until we moved to this new class of materials, polymers, where we were able to really take charge and use glass transition temperature in a meaningful way to impact our everyday lives. And so a lot of you know, science goes into engineering materials around this glass transition temperature. So one really cool thing is like implantable stents, you know, in the human's body. So like a stent keeps a blood artery or blood vein, like, you know, open. If your veins are collapsing, that's bad. So the stent itself has to be, you know, it has to be rigid, right? It has to be rigid. So let me see if I get this right. Right, so when you insert the stent, it has to be strong and rigid, but it also has to, like, you know, when you poke yourself, right? You don't want the stent to like puncture the vein once it's in there. So there does have to be a degree of flexibility. So if we can engineer a plastic that at room temperature is brittle, right? So that's 22 degrees Fahrenheit is brittle, but in the human body is ductile. That way, when we insert the stent, we can have the stent be rigid. So we place it very precisely where it's supposed to be. But then as it equilibrates the human temperature, it will become plastic and flexible and be able to respond to being, when you fall over or when you push up against something or whatever, And that way the stent doesn't puncture the vein that it is supporting. So a lot of interesting biomedical sci-fi stuff goes into ideas of controlling crystallinity and glass transition temperature in polymers to save lives or do something like that, make a lot of money. Yeah, so that's polymers crash course. And I think that is okay for today. But the exam is tomorrow, so good luck to everyone. I hope everyone does well. I will be available throughout the day, so if you do have any questions, last minute questions, you can email me and I'll be more than happy to answer them. But I guess I'll leave it at that, unless anyone has anything else they would like to talk about. Ooh, okay. All right, well, good luck tomorrow. I'll see you later.